Welcome to Kill Aggregate Volume 2. If you are here, probably watching Volume 2, you already know the main character of our story. So if you don't, let me introduce you, Bill, or to better say, the aggregate pattern. So what you all probably want to know is the aggregate dead or alive? So to answer to this question, I want to do some steps back to review what happened before, starting from why the aggregate was introduced in the first place. So take a close look at this code. And we are building a system for managing a school, and we want to subscribe a student to a course. And the course can accept only a certain number of students based on its capacity. So based on your experience, do you think this code is safe, or it might hide some pitfalls? Who think it's safe? Okay, nobody, good. And who on the other side thinks that it might present some issue? Yeah, a lot of people that don't think. Okay. So, of course, the answer is, it depends, right? If this code is, so if we are building an application that does not allow any parallel processing, of course, maybe we can consider this safe, but commonly, typically, this is not the case, because between reading and writing, some other threads can access to the course data and changing it under our nose, and potentially invalidating our rules about the capacity. So a common solution to this problem is to rely on a centralized component of our infrastructure, the database typically, and ensure the access to the data exclusively to one process, queuing all the other processes trying to access the same data. And this is known as locking. So now the problem is to determine what we want to lock. So depending on the technology we are using, the lock can be more fine-grained or large-grained. For example, you can lock only the record, the cursor record, and in this case, the threads accessing to the same course need to patiently wait for their turn to access the data. In other situations, we may be forced or limited to lock larger portion of data, like, for example, an entire table. So it's evident that the way the data is partitioned is crucial, because the larger the portion of data locked, and the lower the parallelism that is allowed, and consequently the performance are lower. So the problem to solve is simple. Find the right technology to lock the right partition of data. But in a modern system, the domain model is often so complex and intricate that finding the right locking partition and locking technique, locking strategy for each use case can easily turn into a nightmare. So the aggregate pattern tried to solve this problem on a different perspective. The aggregate pattern basically prescribes to split your domain model in clusters of associated objects that we need to treat as a unit for the purpose of consistency, right? For the purpose of data changes. So they represent the consistency boundaries. And between members of the same aggregates, you can enforce strong consistency. So strong consistency is needed, is typically required for those rules that are really, really important for your business, so important that you don't want to violate them, even for a millisecond. And typically, developers like strong consistency because it allows for a simpler mental model. On the other hand, strong consistency is harder to scale, because you need to synchronize the access to the data. On the other side, all rules that spans aggregates will not be expected to be up to date at all times. These rules will be enforced, yes, but eventually. So the system could pass through many temporary inconsistent states before to reach the consistent one. And eventual consistency then requires the developer to deal with these temporary states, right? To consider them as possible and to deal with all possible ramification and to write more complex application logic for this reason, right? So eventual consistency means to make decisions at the best of our knowledge, accepting the fact that conflicts are possible, even if rare, and dealing with these conflicts later on, so with additional processes or business logic. For this reason, it allows more scalability because it doesn't enforce synchronizing access to the data. So with Aggregate, basically, we move the space of the solution from the technical space of finding the right locking partition to the modeling space of finding the right boundaries of our aggregates, because the aggregate becomes our default partition. So with even sourcing, the situation becomes a little bit more complicated. Defining even sourcing is not an easy task, since it is not a single pattern, it is a series of practices to ensure data consistency in an event-driven system. So, in an event-sourced system, data are stored as a sequence of immutable events. Immutable is important here. So aggregates can be even sourced from the stream of events that affected them in the past. Basically, aggregates are projections of the event that happened in the past. Nevertheless, they need a special treatment. They are not like any other projection. The reason lies in the mechanism used so far to ensure the consistency of an aggregate in an event sourcing system. So even if all the events are part of the same global stream, in order to enforce the lock on the aggregate, they have been typically stored in separate substreams, one per aggregate. So the substream itself can be easily locked, and in such a way the aggregate consistency can be protected, right? So the obvious consequence of this approach is that each event must belong to one and only one aggregate. And the aggregate is not only responsible for validating the event, but it's also responsible for, it also determines the substream where this event is written physically. And this technical requirement causes an important drawback. In a system where events are immutable, since they represent the fact that have occurred in the past, the strict coupling leads to significant rigidity in the aggregate boundaries. If you cannot change the events that happened in the past, then refactoring the aggregate becomes really, really hard. And this rigidity can increase the risk associated with design mistakes, right? So, because you cannot fix them. And what happens if you design your aggregates in the wrong way? So if you design too large aggregates, you can end up with unnecessary lock and coupling. For example, if you focus on the nouns, for example, on the entities like the course entity, you may end up putting all course attributes in the same aggregate. And that means that unrelated requests, like, for example, renaming a course and changing its capacity, will compete for the lock on the same aggregate, even if it is not necessary. So this can result in higher contention and so in bad performance, but this can also lead to coupling because it hides the fact that those attributes could even belong to completely different bounded contexts. So, on the other end, thank you, if your aggregates are too small to guarantee an invariant, to guard an invariant from one single use case, then you could end up with additional complexity. Let me be more explicit here. in many situations, this is exactly what you need. So this could perfectly match how your business works. So sometimes this complexity is not coming from the processes that your business has. So it's not coming from the business itself, from a business requirement, but it's just coming from a technical limitation. So the point is that finding the right aggregates boundary is super important, but at the same time, it is difficult. So why it is so hard? Why is so difficult to find the correct boundaries for our aggregate? One of the most common mistakes is to design your aggregates around nouns. So using entities and value objects as consistency boundary. The fact is that in many cases, they are not. Indeed, many times the consistency rules that we want to enforce cross the boundary of entities and value object in an orthogonal way. Focusing on consistency rules is the key, right, that help us to detect the right boundaries. Anyway, there are some situations where those rules overlaps in such a way that make really difficult to identify how to separate the elements involved in the validation. So I want to show you a couple of examples. Let's say that in order to subscribe a student to a course, we need to enforce two invariants. So the student cannot subscribe to more than 10 courses, and the course cannot accept more than 30 students. So in order to validate those invariants, we need to know the student subscriptions and the course subscriptions. Since the system can receive any possible combination of students and course, the only solution with a traditional approach is to define an aggregate that contains all those informations. The number of active subscriptions for all the students and all the courses. And this effectively means to sequentialize all the subscription requests. And depending on the specific context, this design could cause scalability issues. So alternatively, a long-running business transaction can be introduced to coordinate the two invariants. And this solution is perfectly fine. And in many cases, it describes exactly how the real world, so what really happened in the business domain. So, however, it also means to treat the initial condition not as invariants. So we moved in the territory of eventual consistency here, right? With all its pros and cons. So let me do another typical example of this same problem, the infamous uniqueness validation. So let's assume that we want to validate the uniqueness of the username associated with an account, a system account. The account can change their username, and once the username is released, it can be claimed, maybe after a delay. Similarly to the previous example, when the system receives a request to create a new account or to change the username of an existing account, we need to know all the username states to guarantee that the new account that we want to claim is not already claimed, so it's available. And also in this case, the solution is to define an aggregate containing all the usernames with their state and the associated accounts. So effectively, this means synchronizing all the accounts creation on a single aggregate. So how we can address the problem without creating this contention? So, as always, it's paramount to use the right tool for the job, and in this case, we need a katana. So the katana is called dynamic consistency boundaries. And DCB is essentially an implementation of optimistic locking for event sourcing. It is a technique to ensure strong consistency without being tied to rigid aggregate boundaries. So DCB leverages the natural, let's say, the sequential nature of the events in a bounded context. All events are stored in a single stream and per bounded context, and all events are identified by a sequence position that is monotonically increasing. 0, 1, 2 are sequence position, and they are identifying the events as well as defining the order of these events in the stream. So each event is also annotated with 2 key attributes that allows for fast filtering. So the event type that identify the event schema and the business logic to handle that type of events. For example, student created, student subscribed to course are event types. And the second is the tags, are called tags. They are used to reference the business instances affected by the event. So the combination of type and tags allows to efficiently filtering, querying the event store in order to reconstruct the precise subset of events needed for a specific use case, a specific decision logic. So let's say, for example, that our component requires certain data to validate a request. So the yellow funnel represents the query, the combination of type and tags for filtering only relevant events for the specific decision the component is making. The relevant events are selected and sent to the component that use them to reconstruct the domain model it needs to make the decision. And when the last event is reached, the event store notifies that there is nothing more so far by sending to the client the sequence position of the last event of the event store. The client keeps track of this position, and I call this position save point, and you will understand why very soon. So while our component is thinking and doing its own stuff, other processes in parallel can publish events in the event store. So once the component finalizes the business decision, it wants to publish the resulting event. But instead of invoking the append API to append a new event, it invokes a conditional append. So the conditional append works in this way. The client sends to the event store the event to append together with a failing condition. The failing condition is composed of the save point and the filter initially used to select the relevant events used to build the decision model. So this is basically telling the event store, append my event, but please don't do that if something new happened, something that I'm not aware of that could affect my decision. Be aware that I am up to date until the save point. So the events that I'm not aware of are those after the save point. In practice, we define a safe zone containing the events that have been already filtered and sent to the client, and an unsafe zone containing the events published after the reconstruction of the decision model. This is the core of the optimistic locking. So the save point represents the limit of what the client used for building its decision model. All events up to that point have been already taken in consideration during the decision-making process. Only those events that are newer, the ones beyond the save point, must be checked to ensure that they do not interfere with the decision. And if there is no conflict, that means that there are no yellow events after the red line. And in this case, the event is accepted, is published. In case of conflict, that is when at least one yellow event is after the red line, the append is refused. So the optimistic locking mechanism ensures consistency even under concurrent access. And this is pretty simple and powerful at the same time. So DCB is nothing more than the technique to enforce optimistic locking in an event sourcing system over a dynamic substream of events. So now that you have seen what DCB is, I believe you have all the elements to answer the initial question. In your opinion, is the aggregate dead or alive? What do you think? Does DCB kill the aggregate? Still in doubt. So despite the playful title, unfortunately for those of you who wanted to see the blood, no, the aggregate is still alive. So it's pretty much alive and there is more. So DCB is fully compatible with aggregates. Adopting DCB does not mean abandoning the idea behind the aggregates. It simply gives you more control on them. For example, with DCB, if you want, you still can map one event to only one aggregate by using a single tag for each event representing the aggregate ID. It's a possibility that you have. And the first advantage that you can have using DCB, also with aggregate, is that you can enforce strong consistency only when it is really needed. So with classical approach, depending on the technology that you are using, when you publish an event for an aggregate, you could be forced to lock it. With DCB, you don't have to. It's up to you to decide whether it's worth it to enforce it or not, by simply deciding which API to use. So in this case, basically, the condition, so if you want to enforce strong consistency, you use the conditional append. If you don't want to enforce strong consistency, you just invoke the non-conditional append. So DCB provides you with more control, making strong consistency optional and contextual, something that you can enable or disable. But the major win is that DCB allows you to atomically update multiple aggregates. How? By dynamically creating a substream of events based on the union of multiple aggregates. Let's assume that the system receives a request to subscribe the student Bastian to history course. And in this case, we want to select all the events related to both the course subscription for history and the student subscription for Bastian. And those events are used to reconstruct the current state, necessary to decide whether or not we want to accept the subscription request. And the optimistic lock is then enforced on the combined tag set. So if there are no concurrent subscription for the same student and for the same course, then the append is accepted. Otherwise, it is rejected. So this prevents the need to introduce a longer business transaction to coordinate the student subscriptions and the course subscriptions. But let me repeat that. The fact that you can do that doesn't mean that you want to that or that you should do that, right? So there are situations where a multi-steps business process is and remains the best solution, the best approach. It is up to you to define the best design for your use case and whether it is smart or not to take advantage of this DCB capability. So DCB is just a technical tool in your toolbox. It doesn't tell you how to design your processes. So just give you more options. And DCB is great with aggregate, but it can also go beyond aggregates. So, for example, by accepting the fact that an event can have multiple tags, we can also elegantly solve the problem of uniqueness validation. For the purpose of this example, let's suppose that in the past, it was registered an account using Bill as a username. This resulted in the publication of an account registered event tagged with the account ID and the username, Bill. After it was created another account with a different username, Black Mamba, and later the first account decided to change the username from Bill to Snake Charmer. So this this resulted in the publication of a username changed event tagged with both the usernames, the one that was released and the one that was claimed, together with account ID. So now, if the system received the request to register a new account with the username Bill, it is simply possible to perform a query for those events tagged with the username Bill. So by reconstructing the current state from those relevant events, we can easily detect whether or not the username Bill can be claimed. So in this case, the system validates that the username Bill is available, and consequently, it proceeds by publishing a new account register event. So could we solve the same problem without DCB? Of course we could. And could we also avoid assigning multiple tags for each event? Yes, sure, we could. We could, for example, decide to explode the registration of a new account in a process, in a multi-step process, introducing new events like username created, username claimed, username released. This is perfectly fine. However, this implies higher complexity, and those events sounds to me more like a technicality rather than a business process. It's not coming from a business requirement. So with DCB, you have the freedom to select the best approach, the solution that represents better your business model. So I hope that this talk today helped you better understand what DCB is meant for and what it is not. There is one main message that I would like you to take away from this session, that is finding the correct boundaries is difficult. Design mistakes are possible, and if you are not using event sourcing, there are several good tools out there to easily evolve your design, but by adopting event sourcing, we lose the flexibility. So the aggregate boundaries became rigid, written in stone. And this rigidity can, it's something that we inflict ourselves by deciding to map the aggregates with one stream. So DCB is a tool for breaking this rigidity, and to break the rigidity of the boundary explicitly in event sourcing system. It allows you to start simple and to increase the complexity later on, if and when the needs arise. And if you discover your boundaries are wrong, then it could be whether because your requirement changed or because of a design mistake. DCB provides you the freedom of fix those boundaries by evolving your design during time. So if you want to know more about DCB, I have good news. 2 years ago, I was contacted by Bastian and Paul, two outstanding professionals. We decided to collaborate to spread and support this technique. And after 2 years, a few days ago, we announced DCB.events. It is a website that explains and demonstrates the concept and collect the most relevant resources around this topic. So Bastian, who coordinated the activity, also authored the 90% of the content, so he truly deserves the credit for this result. And this is a completely free resource that we built in our free time with the goal of keeping these ideas open and accessible to everyone. So we look forward to your feedback. Thank you for your attention.